The idea there is that the brain has very limited access to metabolic resources. Because stress is very metabolically expensive, it puts the brain in an even more precarious state. So it has, a lot of energy that it needs to expend, doesn't have access to those resources. And so it has to triage the resources that it does have.
Could stress be the unifying cause of psychiatric symptoms from PTSD to bipolar disorder and depression? Well, it's certainly possible, and the way stress impacts our brains and the energy allocation in our brains could have dramatic impacts on the symptoms that we then experience. And to talk about this fascinating topic, I'm joined today by Dr. Parker Kelley, who's a PhD and a postdoctoral data science fellow in trauma and PTSD at the San Francisco VA, and also is working in the University of California, San Francisco Translational Psychedelic Research Program. And he, along with several co-authors, including Dr. Martin Picard, who we featured quite a bit on this channel, published a paper, The Allostatic Triage Model of Psychopathology, How Reallocation of Brain Energetic Resources Under Stress Elicits Psychiatric Symptoms. Now, that's a big, long title, but basically the point being that we're under stress, we have limited amounts of energy in our brain, so we have to triage it and put it in different places. And because of that reaction, it may impact our mitochondrial function and may impact psychiatric symptoms. So it's a fascinating discussion, including what we could potentially do about it to help this. So I hope you enjoy this discussion with Dr. Parker Kelley. Now, it is fairly scientific, and we get into some of the details, but the overarching principle is still one that can be really impactful for how we live our lives and how we react to stress and the symptoms that we may experience. All right, Parker, thank you so much for joining me today at Metabolic Mind.
Yeah, thank you so much for having me. Really, really excited to talk to you today.
Yeah, and I'm excited to talk about your paper, which seems so interesting, the allostatic triage model of psychopathology, basically talking about how stress induces an reallocation of brain energetic resources, as you say, so a change in brain energy and how that could lead to symptoms. So really a fascinating paper that you wrote along with our friend, Dr. Martin Picard. So definitely want to get into that. But before we do, tell us a little bit about you. Like, what got you into this field of research to begin with?
Yeah, so my path has been really interdisciplinary. I have a bachelor's in philosophy of mind and another in physiological psychology, and then ended up going to graduate school in biomedical sciences. And it really all started when I was, in the office with my physiological psych professor, and I was with my then friend, now wonderful wife, Katie Venable, who's also an author on this paper, and she asked, why do some people, hold on to like negative energy states? And my professor pushed back. He was like, what do you mean by energy? He had this kind of resistant reaction. And that kind of stuck with both of us for a long time. And we were studying, animal models of stress and trauma. And we kept finding these, data sets of RNA sequencing data with all of these mitochondrial genes. And, we looked at physiological measures and some functional measures, and it just kind of kept coming through. And that wasn't something that the lab previously studied. And so we kind of tested it and pushed a little bit. And, it was just kind of undeniable that there was this metabolic component through which stress was kind of driving these pathological disease states like avoidance behavior in the animals and other things that are, canonically associated with PTSD. And so, I kind of had this. I wrote my dissertation on allostatic load associated factors in PTSD models, and we did some comparisons to human PTSD. And it was just this persistent thing that just kept echoing that question that Katie had asked, and that resistance that my professor had with this hand wavy idea of energy. It just kind of stuck in my mind. And so when I started my postdoc at UCSF with Ifo Donovan and the Thrive Lab and Josh Bowie and the Translational Psychedelic Research Program, I kind of carried this perspective forward and wanted to continue looking at the role of bioenergetics in the things we were doing. And so I started doing psychoneuroimmunology research in human PTSD. And we continued to kind of look at these kind of markers of metabolic and mitochondrial stress, and things kept coming up. And so, eventually met Martin Picard in the first year of my postdoc, and he was super supportive. And ever since then, we've been kind of collaborating on this work. So I'm, a translational neuroscientist by training, but I've recently been wearing the hat of mitochondrial psychobiology, which has just become this incredible kind of lens or map, that helps me navigate and understand these other disciplines that I work in.
Yeah, it's so interesting how mitochondrial psychobiology really sort of bridges so many different fields. But I could see how you could get an eye roll about like, oh, like, energy resources and brain energy and mitochondria. Like, that's not what we're talking about. And that, I guess that was what happened with your professor. But we have to admit we don't know everything, right? So that's great that you're able to team up with Martin and do this research. So, in the introduction to the paper, you talk about psychiatric symptoms, cardiometabolic dysfunction, immune dysfunction, and that those all sort of like come together with stress. So, how good is the evidence linking those three together, the cardiometabolic dysfunction, immune dysfunction, and psychiatric dysfunction? Because that sort of sets up a big part of this hypothesis in this paper.
Yep, exactly. That was the question that we wanted to answer. Is all of these different categories of disorders, these transdiagnostic disease states, are associated with stress, and stress, drastically increases the rate of their occurrence. And these disorders are also highly associated with each other. So if you have hypertension or cardiometabolic dysfunction, metabolic syndrome, these other disorders, it increases your risk of getting major depressive disorder and PTSD, and vice versa. It's our lab recently published a paper showing that there's a strong association between autoimmune disorders and post-traumatic stress disorder, and vice versa. So all of these things are bidirectionally related, and there is really strong evidence supporting these associations, but we don't really understand the mechanisms. We understand maybe this particular immune marker, can drive these particular symptoms in PTSD, in animal models, or there are these kind of mechanisms that exist, but there is no kind of comprehensive model that explains all of these different associations together. There's evidence suggesting these associations, but we don't really know why or how this is occurring.
Yeah, and that's interesting when you talk about mechanisms. I mean, I'm sure there are a number of people who maybe discount the association without understanding the mechanism. Like, no, what's happening in the brain is in the brain, and what's happening in the body is in the body. They're not going to influence each other unless we can somehow draw the connection. So this connection that you're drawing is through brain energy resources and stress. But first, let's define some terms, because you say the allostatic triage model. So what does that mean? What is allostatic triage?
So allostatic triage is another one of these kind of bridging concepts. The idea there is that the brain has very limited access to metabolic resources. It only makes up about 2% of the total mass of the body, but it uses 20 or 25% of the metabolic resources of the organism. And so it's kind of in this very precarious state where it needs a lot of resources. It doesn't have a lot of access to metabolic resources because it's got low capillary density and some other factors. And because of this, when organisms are stressed, stress is very metabolically expensive. Because stress is very metabolically expensive, it puts the brain in an even more precarious state. So it has a lot of energy that it needs to expend. It doesn't have access to those resources, and so it has to triage the resources that it does have to the networks and circuits and processes that are most important to maintain survival, because that's our evolutionary inheritance there.
Yeah, which is so fascinating, right? It goes with this concept of a finite amount of energy. The brain has X amount of energy that it's using, and when all is going nice and smooth, it can divvy it out everywhere it needs. But once that stress hits, and all of a sudden the brain requires more use of energy in certain areas, it's going to have to take away from others. And so the way you described it was it sort of dedicates its energy towards the here and now, like the survival for now, and less about the future optimization. And then that in turn can lead to psychiatric symptoms. So draw that line. When you reallocate brain resources, how can that then lead to psychiatric symptoms?
So we first looked at, which brain regions are most metabolically expensive. So looking at glucose distribution in the brain, we saw an amazing amount of correspondence between the blood flow to different regions of the brain, the amount of glucose they're using, and the actual mitochondrial energy transformation capacity. And so what it looks like is there's this hierarchy where more recently evolutionarily expanded brain regions, particularly frontal cortical regions, are more metabolically expensive than simpler and less evolutionarily expanded cortical regions like the salience network are less metabolically costly. And so what we proposed is that um, in the context of stress, uh, the brain must triage resources from the places where resources are available, right? So if certain regions are really costly, then removing resources from those networks is going to supply more resources than triaging from less expensive networks. And it also kind of corresponds to what's necessary in the moment. The salience network in particular is really crucial for the fear response, and it also mediates a lot of psychopathology associated behaviors like habits and compulsions and anxiety like behaviors. And so what we proposed was that, energetic resources in the context of an acute stressor, are that these resources are triaged from these expensive kind of frontal executive control networks to less evolutionarily expanded, less expensive networks like the salience network. And it turns out that a lot of recent work has supported the fact that the salience network drives a lot of psychopathology associated symptoms. Across numerous different disorders, the salience network is dysregulated in PTSD and MDD and GAD and bipolar disorder. It's dysregulated. So you really see these like it's a strong basis for kind of transdiagnostic psychopathological states.
Yeah, and that's what makes it, on the one hand confusing for many, but also very simplistic. Is like, well, how could, change in energy manifest as bipolar disorder in some, and schizophrenia in others, and depression in others, and PTSD in others, or what? And it's because the brain isn't, in these areas, they can similar areas can manifest differently. So when those areas are the ones with decreased energy, it can be any of those symptoms. I mean, and I guess it is still even a little unsatisfying though to describe it that way, because people want to see the bipolar area of the brain, the schizophrenia area of the brain, right? We sort of want it to be compartmentalized, but it's not. So, I mean, does this model sort of reflect that in any way?
Yes. So we shied away from getting into too much specific detail. My mentors kind of had to hold me back on this a little bit because the paper was already quite lengthy. But we're writing follow ups. Specifically right now we're working on one in regard to post traumatic stress disorder with my wonderful mentor Ifo Donovan. And what we've proposed is that while there are these kind of general shifts from frontocortical, very expensive regions to regions like or networks to networks like the salience network, those general shifts are really contextualized by this kind of developmental process of psychopathogenesis over time. So whether or not this is occurring in childhood in response to like a severe, childhood trauma, or it's occurring in response to chronic stress or, this kind of adverse childhood experiences, ACEs, that particular developmental process of psychopathogenesis determines which networks become kind of over activated in the context of stress and which networks are kind of underactivated. And so what we're proposing is like, depending on when this occurs in, different networks have different susceptibilities. There's a great paper that just came out on this pretty recently, depending on, the time that stress occurs and also the specific context at which stress occurs. So maybe if the stress is occurring, in response to kind of interpersonal or kind of childhood adversity and uncertainty, then maybe the kind of psychopathological state that becomes more likely to develop looks kind of like borderline personality disorder or complex PTSD. Whereas, when it's occurring at different time points and in different environmental contexts, the networks that get strengthened and, through the over allocation of resources to them, and the networks that become weaker in response to less resource allocation to them, that is what generates the specific psychopathological state in any particular case. And so there is, our goal here was to establish a kind of foundational structure on which, we could ask specific hypotheses about specific disorders, and then use these kind of first principles kind of understanding that we've tried to develop here to apply to particular psychiatric disorders to explain those particular symptoms.
Yeah, well, it makes sense and is very complicated all at the same time, but it certainly is fascinating. Now you talked about stress. So, I mean, what level of stress are we talking about? Is this like I'm stressed? I've got a paper that is due in a couple of days, and I'm stressed about it. I've got to get big speech. I've got to get, or like you're talking about the chronic stress that comes from an adverse childhood experience, or just the chronic stress of being in a bad relationship or at a bad job or whatever it may be that compounds over days, weeks, months, years. So what level of stress are you talking about?
So this yeah, great question. And this is something that we really struggled with. Like I just mentioned, this kind of first principles understanding that we're trying to develop here. And in pursuit of something, a model that we can really kind of build up from the ground up, we looked at different definitions of stress in the literature. And a wonderful one, the original definition of stress by the godfather of stress, people call him Hans Selye, is that stress is something that increases the demand on an organism. Very simple, elegant definition. And what we've done is we applied metabolism to that. So we say that anything that increases the metabolic demand on an organism. And there's a more recent definition by Hans Koolhaas. I'm not sure if I'm totally pronouncing that right, but and his colleagues, which said that stress is anything that overwhelms the capacity of the stress response to meet that increase in demand. And so the way we've defined stress is anything that increases the metabolic demand on an organism above the capacity of the stress response to meet that demand. And so that really allows us a kind of framework, right? Because sexual activity, a lot of appetitive activities, things that people like exercise and dancing, they all activate the stress response, but they tend to activate the stress response in a way that doesn't overwhelm its capacity to meet the increased demand. And so what we're talking about here, it driving allostatic triage, driving psychopathogenesis, are conditions in which the stress response cannot meet that demand. So there's, you have a high metabolic demand, the stress response can supply some of that energy, but not enough. And so that gap has to be filled by allostatic triage.
Yeah, that makes a lot of sense. And so I'm sure people listening might be like, okay, but you can't get rid of all your stress. I've been trying stress management. It doesn't always work that well. So what can I do about it? I mean, the stress is there. My brain is going to have to triage its energy resources. I can't stop it from doing that. Or so what does this mean for me? And I know you're not a clinician, you're not giving medical advice, you're not even representing your university, you're talking about your own sort of thoughts and opinions, but I'm curious. I want to hear what you think.
Yeah. So that's a really, really wonderful question. And it's challenging. And yeah, of course I'm not a clinician, like you said, and none of the things that I'm saying here should be taken as representative of the opinions of the VA or UCSF. But there are different ways that we can address this. One of the important ways that we outlined in the paper is predictability. And that's really crucial because we know that unpredictable stressors are some of the primary drivers of psychiatric disease and also systemic and peripheral diseases, because activating the stress, like allostasis is an anticipatory process, right? So the brain, the mitochondrial information processing system, the allostatic and interoceptive system, these systems that regulate energy allocation across the body, they are predictive. And so they need to be able to, anticipate when energy is going to be needed and when it's not. And so activating the stress response when there is no increase in energy demand is extremely costly. And so, this whole process is fundamental to what we think is driving transdiagnostic disease. And so, living in a way where at least a large portion of your life is relatively predictable is an important way to be able to attenuate this kind of anticipatory stress in which you're activating the stress response and you're not using those metabolic resources. So I think that's a really crucial point. And these are things like, eating at the same time, every day, or eating at your relatively similar times, exercising regularly, and just not exposing yourself to chronic, unpredictable and uncontrollable circumstances. I think that's one, kind of fundamental part. There's also dietary interventions that are really crucial. In my post-bac, I did calorie restriction research. And it seems like calorie restriction, it's a great paper by Dan Dixit and some others that have come out since then, suggest that the benefits of calorie restriction may be mediated by ketones, right? And so there are all these different, dietary interventions, from the ketogenic diet to, calorie restriction, intermittent fasting, that can increase blood ketone levels. I think being hungry every now and then is beneficial, and it may be consistent with our kind of evolutionary background as human beings. And for most at least carnivore or omnivore animals, it's a lot of boom bust cycles.
I wonder if you could tie that into just better metabolic health, healthier mitochondria, and then maybe even a better stress response. Like you're talking about is the amount of stress that overwhelms the response. So if healthier mitochondria, better metabolic health can then help somehow that with that stress response, maybe that staves off this need to reallocate energy resources. So obviously a hypothesis, but certainly seems to fit.
Yes, of course. So yeah, that's a great link there. So something really core to our model is this idea of metabolic efficiency, and there's metabolic efficiency at the biological level. How good are the mitochondria at taking this kind of energy built up in the chemical bonds of the foods that we eat and using oxygen to transform that energy into something that's usable by our cells. So without going into too much detail there, fasting or intermittent fasting or calorie restriction or ketogenic diet, these sorts of processes limit these kind of super high spikes in the amount of metabolic resources that are kind of being required to be processed by the mitochondria. So if you have metabolic inefficiency at the cellular level and at the systemic level, this kind of starts to create a situation where the brain and the body are not very good at regulating your systemic homeostasis, and this can drive things like affective dysregulation and what we talked about before, allostatic triage, this distribution of energetic resources. And so so to get back to your question, it's like I think it's really crucial for us to think about and try to find clinically relevant, useful tools like diet and exercise and these other tools that we have to find a way to normalize this kind of metabolic efficiency. And I think what that eventually does is it trickles up to allow the brain and the entire whole organism to be able to better regulate its metabolic health and limit the extent to which allostatic triage and these things are necessary.
Yeah, it certainly makes sense. The better starting point you're at with your metabolic health and your brain energetics, the better you're going to be able to handle this for sure. Fellow mental health clinicians and healthcare providers, you now have access to a suite of free CME lectures on metabolic psychiatry and metabolic health. Each of these CME sessions provide insight on incorporating metabolic therapies for mental illnesses into your practice. These CME sessions are approved for AMA Category 1 credits, CNE nursing credit hours, and continuing education credit for psychologists. And they're completely free of charge on mycme.com. Now back to the video. But the other question of what can you do about it sort of brings in your other passion or your other world of research at the Translational Psychedelic Research Program. So there's been some research about psychedelics and their potential role for stress and the brain energy response to stress. So tell us a little bit about what you've learned there through your research and your experience.
Yeah, so this also started back in graduate school, where we in some of the PTSD models that we were using, we administered N,N-dimethyltryptamine and another component of ayahuasca called harmaline, which is an MAOI. So either independently or in combination to the rats that had been stressed. And we saw all of these changes in mitochondrial gene expression, and we also found that that NN-DMT, or the ayahuasca kind of pharmawaska is what we called it. It's the extracted components of ayahuasca. Also normalized stress-induced reactive oxygen species production. So what we found in the PTSD rats is there's this huge increase in free radical generation in the brain. And after 3 administrations of either DMT or that combination, we saw this normalization back to baseline of reactive oxygen species generation. And most ROS are produced by the mitochondria, at least half in most conditions. And so, in combination with these mitochondrial genes, it looked like there was something going on. We didn't have a causal study, but we had this hint that there was, this metabolic component. We also saw a lot of insulin-like growth factor and other sort of metabolic mediators that were altered. And we compared this data to human PTSD postmortem samples, and we found that indeed, like a lot of the genes that were altered in the animal model were also altered in the brain of human PTSD in analogous brain regions. And they were, I think, 14 of the 17 genes that were altered that were similar to human PTSD were normalized by the ayahuasca administration. I also worked with Professor Charles Nichols at LSU Health Science Center, who's this great literature showing that psychedelics are anti-inflammatory. And it's really interesting because they seem to be anti-inflammatory in a different way than a lot of our pharmacological tools that we currently have, like glucocorticoids or non-steroidal anti-inflammatories, in that they don't seem to reduce inflammation below baseline. I mean, it's there haven't been really great comparative studies out there, and that's one of the reasons I want to talk about this, to get people to maybe try to confirm or disprove this hypothesis. But it seems like psychedelics may be producing immunomodulatory effects and anti-inflammatory effects in a way that's distinct. So it could be a distinct mechanism there, which could be really powerful. And that really important thing of it not reducing of the psychedelics not reducing inflammation below baseline is really crucial, because we're really only seeing those effects in animal models of cardiovascular disease, chronic inflammation, respiratory inflammation, but we don't really see that much in control animals. So you don't have this potential of immunosuppression like you have with glucocorticoids and insects. And you only have to administer them once or twice or 3 times, or even Chuck Nichols, my mentor at LSU, has shown that you can even give very small subperceptual doses of psychedelics and still see this effect. So it may be that the psychoactive psychedelic experience isn't necessary for the anti-inflammatory effects. And looking across all of these different disorders, just like we talked about with transdiagnostic pathology earlier in the episode, all of these disorders for which psychedelics show anti-inflammatory effects are associated with mitochondrial and metabolic dysregulation. So it may be that mitochondria that they may play a role in the effects of psychedelics.
Yeah. So really interesting rodent, like early preclinical research, but we'll see how that expands and grows, and so much regulation around psychedelics. And if it is shown to be safe and effective, hopefully there'll be a path where it can be safely and effectively used in clinical practice down the road. But one last question though before we wrap here is, I liked one thing that you wrote or that was written in the paper, that this allostatic triage model doesn't contradict existing models of psychopathology, but rather adds to it. So I could see someone saying, no, we know it's about, serotonin. We know it's about dopamine. This doesn't have to do with that. So how do you sort of say it doesn't contradict, but rather sort of adds to it?
I'm really glad you picked up on that, because that was, that's a really, really fundamental point here. The idea of, in developing ATP was not to kind of start from the ground up and just build our own thing. We really wanted to integrate and incorporate the existing models out there. I think the problem is we have all these models that explain little pieces of things, but we don't have a comprehensive model that binds everything together. And the idea is that like neurotransmitters, like by and immune cytokines, my Aoife Donovan, one of my PIs, is loves to say that if cytokines were discovered by neuroscientists, they would be called neurotransmitters. And the reason is because these things, like IL-6, for instance, these immunotransmitters, they modulate brain activity, and they can be produced by neurons and lots of different cell types that are outside of the immune system. And I think maybe another level kind of that explains that connection, as well as these other things that we're talking about, is that all of these things are metabolically active. Neurotransmitters like serotonin, like I described previously with the 5-HT2A stuff, they modulate mitochondrial function. Same thing with dopamine and norepinephrine and cortisol and, glucocorticoids. All of these different things have a metabolic role. So it may be the case that, if we start thinking about these things in terms of the way that they change patterns of energy flow throughout the organism, from the mitochondria to the mind and back down again, we may be able to understand what's quote unquote really going on here. Instead of just having these little molecular pathways that are kind of disconnected and everybody's working on different things, we really need a model through which everybody can begin to understand. We need a model like we have in other fields of science, that can really explain things all in one.
Yeah, it makes me think of that cartoon with the blind people trying to describe the elephant, and you can only describe the one little part that you can feel, but you don't get a picture of the whole thing. And I think that's a really good analogy for what you were just describing. Well, I think this has been a fascinating discussion about this whole concept and trying to tie it all together. And obviously, there's a lot more to come, I'm sure, from you and from Dr. Picard and from all your co-authors on this. So if we wanted to learn more about you and follow you for your future work, where can we direct people to go?
Yes, you can find me on Twitter as it's at Sequence by Neuro, and same thing at on Blue Sky is Sequence My Neuro is my handle there, and also post a lot on LinkedIn. It's just D Parker Kelley, and that'd be a good way to maintain awareness of the new papers and perspectives and things that are coming out. And yeah, you could also follow me on Google Scholar and these other sorts of Web of Science and these other PubMed and these sorts of things if you're interested in that. And then I also post this episode and other podcast episodes and things out there. And there also be opportunities to kind of support the research and help out. We're interested in everybody's input too. We really want to develop a kind of community around this, and with and improve our science communication with these things in ways that hasn't really been normal in the past. So.
Well, your passion and enthusiasm and scientific curiosity certainly shine just by talking to you. So I really appreciate that, and keep up the great work. And thank you for joining me.
Cool. Thank you so much, Brett. I really appreciate it. And it's great being here.
Thank you for watching. If you want to see more, check out these recommended videos. Also, if you haven't already, don't forget to subscribe to our channel to stay up to date with our content and help us expand the movement. And if you want to sign up for our newsletter, access our resources, read the latest research, or check out the Think Smart framework, click here to visit our website. See you on the next video.